direction of how we're going to do the research. Initially, we were thinking doing the research also in the wind tunnel, and kind of start thinking on the problems in a different way, and decide to change a bit things. And picking up where Phil mentioned yesterday, we are working in an environment where we have much less resources to do experimental fires in the field. And some of the comments that Jim made some years ago, that we need to think about do more with less fires. And so that's where this research went, and it was supported by the Bushfire CRC, and really need to thank them for being patient and not getting the results we were thinking delivering initially, but kind of changing the research agenda and come with some different product that we think is much more applicable to some of the field applications. This is a problem. It's worthwhile just focus on this. The word fire transition is used in different concepts. What we are talking here about is the changes on fire, vertical transitions between different fuel layers, right? And we have this graph from Alan MacArthur shows, in this case, the transitions as the fire accelerates. This is time, rate of spread. As the fire accelerates, so initially just consuming ground fuels, transitions to higher fuel layers, shrub fuels, and with each transition kind of bumps up the rate of spread and intensity. And Mike Wharton showed yesterday that crown fire model in the Canadian system, where there's really sharp increase in the rate of spread, and as a fire goes from the surface to a crown fire. But at the same time, we can think about this problem from the point of view of, instead of time here, we would have wind speed or FFDI. As the severity of conditions increase, we also are going to see the fire transition from lower fuels to higher fuels and bumping up the intensity. So that's the problem we are dealing with. To kind of understand where we're going, we need to look at the fuel complex, the eucalypt fuel complex, and see how it is structured, right? We move out from the using just fuel load as a descriptor of fuel structure. It worked very well in the past, but as we want to address other issues with fire propagation, we need to start looking at the fuel complex as an aggregate of different fuel layers. We have the surface, near surface, we have the elevated, sometimes we have a gap between the near surface and elevated, and then we have the bark, fuel layer, total different structure, and then the overstory component. Important here is to acknowledge that as we go up in height, there's a change in this bulk density. It's about the fuel amount by unit volume, a porosity, which fuels in the bottom very compacted, heat transfer not very efficient. As you go up, the efficiency of heat transfer increases, which leads to higher rates of spread, right? Also a bit more exposed to wind speed. And so our idea, when we thought about coming up with a model for fire transitions and propagation, and our idea was to come with something like this. So in this graph, we have rate of spread, we have within stand wind speed, we have different fuel layers there. And with these current models, what I mean is the models that are normally used, right? We have, as wind speed increases, we have a continuous increase in rate of spread. What we want to get is something that, as wind speed increases, we have this continuous change in rate of spread from only surface fuels being involved in combustion. When you start engaging near surface, the fire spread bumps a bit higher. Goes to elevated fuels, a bit further higher. And these changes depends, essentially, all the magnitude of the changes depends on the fuel structure. In this case, we might have a 50% increase. In some cases, it might be a double or triple of rate of spread that occurs when these changes occur. These changes happen. So the research objective we had, for once we wanted to understand the factor or the processes that are driving these fire transitions. We want to quantify them, and we want to develop a model, essentially, that we can use that will quantify rate of spread, all rate of spread changes in intensity as the fire goes from a low intensity surface, the fire severity increases to almost a ground fire. Now, this is how we see the problem. And this also goes back to that assumption that, or call it assumption, but what Phil mentioned, that when you have a fire spreading, the fire is going to spread on the top of the fuel layer. So this is what transports the combustion wave, and then at the same time spreads downward to different fuel layers. So picking up a bit this idea, this graph what we have is increasing wind, decreasing fuel moisture, essentially increasing FFDI from the left to the right. You know, mild conditions, you only have surface fuels being consumed. As severity increases, you start to have near surface and surface fuels involved in combustion. Then furthermore, elevated near surface fuels, and you kind of have to feel what's happening, right? What our big assumption in here, to simplify the process, is that the top layers, the ones in bold, are really ones that are driving propagation, right? Sustaining the flame. The other ones are also contributing to energy released, but where the flame is spreading is on these top fuels, right? It's a bit like because they are finer, higher heat transfer upper in the upper layers, is the fuel that offer the path of least resistance, allow the fire to propagate a bit faster, right? And we did a bit of this work when we yesterday showed some of the Malahis models, also considered surface and ground fire propagation. We did the same for conifer forests, where you have the surface fuels and ground fuels. But in this case, so we are interested in applying to not just from surface to ground fuels or understory fuels to ground fuels, but all the sublayers of fuels in the understory. And here's where we kind of changed the shift of our research. Because to do something like this, we need to have a model for upward heat transfer, tell us the energy from the combustion of fuels on the lower layer, how much goes up as it's going to ignite the fuels above. But at the same time, we need to have a model for propagation. And we didn't have any model that will allow us just to have, for propagation, just surface fuels, or just near surface, or just elevated, right? None of the models we use, MacArthur, the Vesta, the Red Book, etc., goes to just use one of the fuel layers. So what we did, how we start the process? Well, first we need to go and develop a mathematical theory of this different process of fire propagation. Essentially, we are building a physics-based model here, and our idea was to apply a modular bottom-up framework, modular on the basis that we have a lot of processes, a lot of things happening, and there's a lot of things we don't know about fire. One issue with fire behavior, when you think about the fundamental aspects, is that it's very difficult to measure, right? Talking about radiation from a fire, talking about the wind that's generated from a fire, or even temperatures from the fire, all very difficult to measure. There's very few measurements, and because of that, very little understanding of what happened. And so you're going to, by using model, allow us to use the best we have now, but also later change to something better as we work. As we did this work, we discovered a lot of components of the fire propagation process that we can, in the near future, improve from field measurements. And so we expect to fill up these black hole knowledges with some new models. We want to include key combustion and heat transfer mechanisms. We're talking about radiation and convection, how the fuel consumed determines the flame structure and things like that. And again, yeah, identify what knowledge gaps, what we need to know to make this model work, right? And so that's where we're going to link this physical approach with the field data, because there's a lot of things we don't know. And so the idea was, well, let's go back to some of the previous fires, namely the Vesta experiments, and get some of those fundamental combustion mechanisms, and then kind of close the model. So what things we need to know to build this model? We need to know how much energy is released by the fire, right, for each of these fuel layers. How much that energy is going to determine the flame structure. And we were talking about here earlier about this dip, right, dipping on fire propagation in some of these experiments. So it has to do with this energy in the fire makes the flame standing, and the flame structure in its angle is always a balance between the wind and the buoyancy in the fire. And when you have those we start an experimental fire, we don't have much buoyancy yet because the flame front is thin. So the wind is really driving the propagation. But as the fire builds up, we have more buoyancy, and so it changes the flame structure and the heat transfer. So we need to understand that. Again, because we're talking about the ignition of the fuels in the canopy, we need to build have a model that describes the structure of the plume, how much energy goes in that plume, and how is that going to affect the ignition of the fuels. And these really all the components, and in the end we determine radiative and convective heat transfer to those fuels and determine if they ignite or not. There's basically the equation we use, that's a simplified form. Essentially, the rate of spread is a function of the energy being released by the active combustion and the energy required to ignite the fuels. Excuse me. The denominator is quite the simple part is really a function of the fuel size and the moisture content. And the top is where we are taking into account the radiation heating, convective and convective cooling. And this equation is used quite often. And it is on the way that you're going to populate that top part, how you describe the processes that's going to determine how successful we're going to be with this kind of modeling. I'm going to play again that video from yesterday from Phil, and I wanted to look at where the wind is going, right? Where the air is going. I need to do it here. And this has to do with this convective and radiative heat transfer. So don't think so much about Bushfire, but as they ignite, you're going to see where the flow of the air, where the air is going, right? For most of the time, the flow, the main fire, it seems to be pushing the support fire into it, yeah? So and this has to do with this, this convective cooling. For most of that video, what you see is that the wind, although the fire is spreading in one direction, the wind, those spot fires, is coming into the fire, right? So what happened is that all air around the fire is cooling the fuels that are being radiated by the flame front, right? So this is one of the processes that we want to really capture. The other video is here. Video. Okay, yeah, I go to my folder. Why is it important? Because it's important because it's about what's driving. For us to be able to model well, we need to know really what's driving the fire. This is a bit dark here. This is a malleus burn, but you see it gets a bit darker. But just see how the flames are propagating and are like they are being pushed by something from behind and like licking the fuels and igniting the fuels. Total different mechanism, as you see in these two fires. In the previous fire, at the flame front, we didn't see the flame front approaching, but as the flame front was approaching, the fuels were really being cooled by the air, whereas the other fire, we could see that convective transfer or advection was impacting the fuels much earlier. And this goes back to this balance between the fuels being consumed and the buoyancy in the flame and the wind speed, right? There's two regimes here, like, let's say. So we need to capture these processes to, if you want to model the fire. And so we have all these things incorporated to the model. I will not show any equations, but see, that's the things we want to capture in the model. And how the model works is like this. We have different fuel layers. Firstly, we determine the rate of spread for the bottom fuel layer, let's say the surface. Then we need to determine if the amount of fuel that's being consumed is enough to propagate a flame. If not, there's enough fuel, it's not enough fuel there, the fire will self-extinguish. If yes, it's possible, then we're going to calculate heat transfer to the fuel layer above. And if say, okay, the energy from the surface fuels ignites the near surface, then yes, we have ignition, we calculate this again. Do the same thing for the surface, for the near surface fuel layer. Same process, we get to the elevated fuels. Yes, or let's say no, we didn't ignite the elevated fuels, and then the rate of spread is given by the near surface fuel layer. So this kind of a process, like an iterative process. So for these, yes, we need to, we would like to call it a model system. There's a lot of things we need to know, because essentially we have a fire, and we need to characterize the fire as an energy source, and for that we need to calculate all these properties of the fire, the reaction time or residence time, and the flame depth, the flame geometry, height and angle, fire line intensity, flame temperature profile, how the temperature changes with height in the flame, and the flame maximum temperature. So for these, we use a lot of models that have been developed, like for these two models that Mike Wharton developed when he was working with investor burns. And so this defines really what a fire looks like, and determines how much energy is being released, and it calculates radiative heating from the flames, its flame radiosity, and then the key unknown to close this model is really this air temperature and velocity. In those videos, what we could see is that it's convection that's driving the fire, right? And convection is not just hot air, but it's also flame contact. So when very hot gas, flames, very hot gases, when they touch the unburned fuels, how that energy is going to transfer to the unburned fuels. So the big unknown that we have is how air temperature and velocity change ahead of the fire. In one of those fires, we had a lot of inflow into the fire, and the other one we didn't add that, and we don't know really why. So we want to capture that. So what we did, and that's where the part where we're going to So we build the formulation, the mathematical formulation now, but there's a lot of things we don't know very well. So for the model to run, we need to find these little tidbits. So we want to model this convection. What we did, Mike Wharton provided us all this data that we collect during Vesta, during two seasons. And what Mike did was have some towers, thermocouples, so he was measuring temperature at different heights in the flame zone and above the flame. So in the end, we get something like this. This is what we call a temperature time profile, where we have time as the fire approaches, lower temperatures, and the fire reaches about 600 Kelvin, this is 300 C, the rapid increase in temperature because the flame arrived, and then it kind of decreases slowly. Now, we can, if we know rate of spread, we can transform this time as a distance from the fire, and that's what we did. And so we count this, as you see, this zero, this, let's say, is the location of a fuel particle, and as the fire approaches, the temperature is increasing, right, until it reaches the fuel particle. So the key for this modeling approach is to characterize this increase in temperature. And Wendy, a few years ago, looked at this concept of this characteristic eating distance, which is a parameter that's giving us the shape of this curve. Depending on certain conditions, you might have a flatter and rapid increase closer to the fuel particle. That will be the example of that burn in the Vesta you saw. And other conditions, we have a more curves more higher temperatures, right? So we picked up all these data that Mike provided us and did some analysis, and what we did was able to model this characteristic eating distance, this parameter that defines the shape of this curve as a function of the height where we are measuring. So this will be an example for elevated fuels, 1.1 meter tall, one for near surface fuels, and this one for surface fuels near the bottom. And you see the different shapes mean that the higher the fuel, the sooner they will see higher temperatures and the faster they will ignite. So it explains a bit of that faster rates of spread for fuels located higher in the fuel bed. So we're able to measure this, to model this curve, this aspect as a function of height and wind speed, and also as a function of the ratio between the energy being released by the fire and the wind speed. That's also what determines the flame angle. So we put everything together, and we start doing some validation simulations. This is one of the Vesta fires in DV. That's the low shrub location, right? 6-year-old. We have 13 kilometers per hour, open wind, fuel moisture about 6.5, fuel age 6, surface fuel height very low, pretty much full cover. Near surface fuel height and elevated, not very high, but very open, so very low cover values here. Observed rate of spread 3.2. We got with the model 2.1, an error of 34%. Well, that's pretty good, because when you put all these different models and all things give a sensible result, that's pretty good. A different simulation, 20-year-old fuels. You see higher coverage in the fuel in the near surface, and elevated. Observed rate of spread about 11, predict 9. That was a pretty good prediction for my standards, at least 12%. Very good. When I get 12%, I go home. And this one, different site, the high shrub site, you see higher cover, taller shrubs, 40 meter per minute. Rate of spread, we got a value of 21, 50% air. Well, that's not too bad either. Anyways, we go and as Jim, also Jim is a preliminary model. I'm also a preliminary model. So a little bit things to improve, anyways. When you in this graph, you show the observed rates of spread that predicted for the Vesta, at least a subset, and we get some really good predictions, and we have a lot of under prediction there. The few fires under predicted. Yeah, we need to look into that. This is also a course, a bit of a course simulation. And another thing that's not here is that is a plot of the residuals, and you see they are truncated at about 4 kilometers per hour of understory wind. The issue is that the model is not converging for those lower winds yet, so we need to work a bit more on that. But for the rest, it's working well. So still some work to do. And partially is that, again, the more we do, in terms of the physical aspects of fire propagation, the more we realize we don't know much, right? And so in terms of future work, there's some validation that we need to do, some of the components. I was just showing some validation against wildfire, some fire propagation, but we want to know also all the sub-models, how good are they? Are they contributing too much air or not? So we need to look at the radiative component and other things, and then the knowledge gaps. Just as an example, we have our flame radiation sub-model we're using here. It was a model developed by Mike Warden a few years back, and we also compare with the East model with some shrubland data, and so that was very sensible. So because of anything else we applied in our system, but we better look and see how well it's behaving. And right now we are developing the instrumentation to conduct this kind of validation in the field. Now, aspects fuel particle eating. When you look at the physical aspects of heat transfer, we tend to consider live fuels as very moist fuels, right? But you know that if that fuels are very moist, they don't burn, but live fuels with the same moisture content, they burn. So there's something there we don't know. So that's something also we need to get a better understanding. Going back to Phil's comment yesterday, it's not the total fuel load that drives the fire. Total fuel load has worked very well for the framework of modeling framework we've used in the past, but when you look at a physical approach, you can only consider the fuels that are consumed in flaming combustion. If not, you are inflating the energy that's being released by the fire and giving you errors. So this fuel consumed in flame combustion is a function of fuel dryness and the heat flux. So you need to determine, but also this depends on the flame height, depending on the heat flux. This determines the flame height and how this balance between the fire and the wind, which determines the fire itself and the heat flux, which all goes around. And it's quite a difficult. So it's not really just a fraction of the fuel load, because it's this fraction, it depends on also all the amount of fuel that's burned. So if you have only 500 grams per square meter, it might be all the fuel is consumed, but you have 3 kilos of fine fuels per square meter, or 30 tons per hectare. We know that not all the fine fuel is going to be consumed in flame combustion. But there's all these issues. We need to get a better understanding. And the other one we thought was the biggest unknown is this: when we talk about convective heat transfer, this little simple formula, but none of the formulas that are used have been determined for wildland fuels, and you just use things that have been determined in the laboratory for other applications. And we were going to look at literature, there's several of them, but they all give a very different results. So it's a bit like a pick and choose. We don't want to pick the one that fits better to our data. We want to pick the one that's more realistic, right? And so that's something we need to do more in the laboratory as well. And as you see here, wind speed is the biggest driver on this convective heat transfer. But the wind speed above the fire is the biggest unknown. Here's a plot again, some work from Wendy. Wendy did a lot of the work I used, just in here. This is again, we have imagine you have a fuel particle at 0, and this is from a wind tunnel, and this is the wind speed. As the fire is far from the fuels, you have this is the average wind speed, right? It's about the wind. The wind is the wind tunnel wind. As the fire approaches, the wind goes about to nil. So there'll be like a conversion zone where there's no wind. And you see the light lines. So the black is the average light to the real wind, and some of them are negative. So it's opposite to the direction of the flow, right? So it's cooling the fuels. And then as the flame approaches the fuel, that wind speed increases to a value much higher than the average wind speed, right? So we need to, we don't know what happens in the real fire about this. When you did some work in the wind tunnel, but in open conditions, things might be a bit different. So that's this is probably the biggest unknown. And the other one is the big question, you know, come here and present this messy model, and how can we apply this model, right? And the idea we have is to link, again, these fuels, this description of the fuel structure with the Australian fuel classification that Jim talked a couple days ago. When you devise the fuel classification, the idea is that it's not tied to any existing models. We don't want to have the problems that Bob Keane mentioned yesterday. We have a flexibility that allows to, whatever models come, we are able to apply that to the fuel classification. And so the idea is to have for each of the fuel types we have in the classification, at each of those layers that Jim mentioned, have the tabulated values of fuel load that they cover for each fuel layer. Again, goes back to if you have a top tier with a lot of uncertainty, you might have some values, but a lot of uncertainty because there's a big range. As more work you do, you will narrow the quantities that are describing the fuel type. You know better the fuel type, and the simulations will be better. That's what I have about this work, and I'll be happy to answer some questions.